Let's now talk about omega notation or big omega notation. This is opposite of big O. Big O notation is mainly used when you have an upper bound, and big omega notation is mainly used when you have a lower bound. Let's consider an example to understand application of omega notation or big omega notation. Consider a situation where you have an algorithm to implement an online game, and say there are n players in the game, and this game keeps on running forever until unless a player quits the game. If a player quits the game, then the game is over. Now you can't say anything about upper bound on the time taken by the algorithm or program because it keeps on running, but you can have a lower bound. Suppose your algorithm is initializing scores of n players, then you can say the time complexity of this algorithm or this program is big omega of n. It's going to take at least big omega of n time because there might be running a loop which is initializing scores of n people, right? So it's going to take at least linear time, and we don't know the upper bound, right? So big omega notation is useful when you have a lower bound. Consider another example where you are supposed to print permutations of a string. So if you have a string with say 3 characters, then there are going to be 6 permutations. In general, there are factorial n permutations. Whatever algorithm you write, it's going to print those factorial n permutations, right? So you can say the algorithm for printing permutations is going to take big omega of factorial n time, right? Because it's going to generate and print all these permutations on the screen, and there are factorial n permutations, so you need at least this much time. So whenever we use big omega notation, we use it to indicate a lower bound on the time taken. If you take a closer look at this mathematical definition of big omega notation, it's opposite of big O notation. It says that Fn is big omega of Gn if and only if there exists constant C where C is greater than 0. See, this condition C is greater than 0 is there in big O notation also, and n naught where n naught is greater than or equal to 0. And we discussed in asymptotic analysis video, whenever we talk about functions, we always talk about this first quadrant where n is greater than or equal to 0, and Fn and Gn are also greater than or equal to 0. So this condition applies everywhere whenever you talk about asymptotic notations or asymptotic analysis, such that Cgn is smaller than or equal to Fn. So this is just opposite. What we were saying in the big O notation, we were saying Cgn is greater than or equal to Fn. Here we are saying Cgn is smaller than or equal to Fn. That's the only difference. And this part is also same for all n greater than n naught. See, this part is going to be everywhere. We talk about always large values of n when n tends to infinite. So if we find a value n naught after which this condition is true, then we use the particular notation big omega or big O. Let's take the same example. Let's say we have Fn equal to 2n plus 3. And please remember, for big omega notation also we can use the direct method. What we do, we ignore the lower order terms, we ignore the constant of the highest growing term, and we say this is big omega notation, because big omega also means equal or lower. So if you see this example, you can ignore 3, you can ignore this constant, and you can say big omega of n. But you can also write it as big omega of 1 or big omega of log n, because smaller values, smaller growing terms are also fine with the big omega mathematically. But when you know the exact bound, why to use smaller bounds, right? The same reason as big O. Let's take some more examples. For example, if you have 5n square plus 4n plus 6, you can simply ignore the lower order terms, ignore the constant of the highest growing term, and you can say it's omega of n square, big omega of n square or omega of n square. See, order of growth is n square for this expression. You can either use big O, you can use omega, or you can use theta when you know the exact order of growth, right? So this is clearly big omega of n square. However, you can write it as big omega of n also, right? Similarly, you can write it as big omega, big O of n cube also. In big O, you can write higher growing. In big omega, you can write lower growing terms. Okay, so this is the direct method, right? We can directly say it's big omega of n. Let's see how does this formula valid here. So we take c equal to n. See, what we were doing in big O, we were taking the constant of the highest or growing term, which is n here, and we were taking one larger value. Here I've taken one smaller value, right? because when n tends to infinite, this is the term, the leading term is going to be the most dominant term, right? Even if you have larger expression n cube plus n square plus n plus something something, n cube's multiplier or constant would be the most dominant term, right? So we take c equal to 1 here, one smaller value, and we try to figure out n naught, and we get minus 3 greater than or equal to n. And since we talk about first quadrant only, we don't take the negative value. If this is true for all values small greater than minus 3, that's going to be true for all values greater than 0 also, right? It's going to be true for minus 3, minus 2, minus 1, 0, and all the upcoming values. So we take n naught as 0, right? So we have found n naught, we have found c equal to 1, and this formula is valid. So we can say mathematically also that Fn is big omega of n. Before we talk about some more facts about big omega notation, please go back and check the graph that we drew for big omega notation. In the graph, if you notice, c of gn always has value is smaller than Fn, right? For all values of n greater than or equal to 0, right? From 0 itself, c of gn is smaller. This is opposite of big O, right? In the big O notation, 3n was having greater value than 2n plus 3 after certain value of n naught, and that value was 3. In big O notation video we saw in the graph. So in the big omega notation, we just need to find an n naught after which c of gn is smaller or equal. In big O notation, we just need to find a value of n naught after which c of gn is greater or equal. Let's now see more interesting facts, and these are similar to big O notation facts that we discussed. If you see these terms, these three terms have exact order of growth as n square. So we can say the value of these terms as big O of n square, theta of n square, and big omega n square also. See, exact order of growth is covered by all the notations. Big O covers smaller order of growth also, right? Big O of n square means you have n square order of growth, or you have the terms which are smaller than n square order of growth also. And omega covers greater order of growth also, right? But exact is there in all three, right? So we can write all these three terms as big omega of n square. And with big omega, you can write higher growing terms also. Like this is order of growth n cube, but we can write in big omega of n square. In fact, you can write it as big omega of n and big omega of 1. That's why I have union here. This u means union here, right? So this set, this set, this set, they all can be written as big omega of 1. In fact, any time complexity can be written as big omega of 1. Big omega of 1 means either constant or higher than constant, right? So any algorithm that you have will either have constant time taken or will have higher than constant time taken, right? Let's now see this one. This one is this term has linear order of growth. This one also has linear order of growth. So they all are covered by big omega of n, and big omega n covers these also, equal or higher growing polynomials. These are all constant terms. This is constant, this is constant, this is constant. So they are big omega of 1, right? And big omega of 1 covers everything, right? I have union here. So these are examples of big omega notation. Now, last thing about big omega notation, if Fn is big O of Gn, then Gn is big omega of Fn, right? Because they are opposite of each other. If one function is having order of growth smaller or equal, right, then I can write it here with big omega notation.